Okay, can everyone see the paper?
Yep.
Okay,
Yes,
great. So I'm going to be presenting this paper called Binarized Neural Networks today. It's an older paper. It's from 2016, like relative to machine learning years. But like it's from 2016, but it's actually like a really highly cited paper. I think it has something like 3,000 citations, or let's check on Tribune. Yeah, 2,500, about a little bit more, which is a lot for a paper. And it's a paper that I came across because, again, of this project that I'm working with Tanya on, there was an argmax operation that had to be differentiable, which I didn't think was possible. And then, and it's not, but you can approximate it, make it approximately differentiable. And so we found this trick and we're like, where does this come from? And it doesn't even come from this paper, but this is the first paper that introduces it, because where it was originally introduced was in Jeffrey Hinton's lectures, like, I don't know, 20 years ago or something. That's where it came out first. But this paper is about binarizing a network in order to make it more efficient at inference time, and also like more memory efficient, more compute efficient, with the hopes that like we can compress these like really large networks down to a point that we can put them on a mobile phone. And having read it, now that I've read it, I'm wondering if the reason why it has so many citations is because it's like the paper that everyone who does work on quantizing LLM cites. Because it does kind of, it feels a lot like quantization. Well, it is quantization work. Let's see, is there anything I want to say before I start going through the paper? I'll just repeat myself just to make sure. So like the reason why this paper is, the focus of this paper is on compressing down a neural network and making it fast enough and performant enough at the same time to be put onto smaller devices. The main contribution of this paper is they figure out how to binarize everything, or almost everything, about this network, like not only the weights, but also the activations in the network, and do it at training time and test time. Although I actually don't think I saw, from like a performance point of view, the necessity of binarizing at training time, but we'll get into that. And then kind of the structure of my presentation will be, first we'll go through like the technique itself, then we'll go through the results, and I'll try to go through like each part of the technique in a little bit more detail. One thing I like about this paper is there's no theory in it, or yeah, I mean, you could argue maybe a little bit, but like really no theory in it. And it's more of an empirical paper. Like they provide no real justification for the things they do and like why they're a good approximation. I was even wondering if this paper was submitted today, whether like NERPs would still consider it a good paper, because I feel like these days you have to have some kind of theory backing all the things you introduce, or you just have to have like such amazing performance with respect to the rest of the field that they're willing to accept it anyway. Okay, let's get started. So section 1, the method, binarizing a network. So as I said before, the thing that's different about this paper from the previous papers that was about it, on it, is on this topic, are that they're not only binarizing the weights, they're also binarizing the activations, and they're doing it at training time and test time instead of just test time. So they have two binarization functions that they use. One is the simple, like the sine function, which you can see over here. And then the other one is this stochastic binarization function, where you actually have to sample from some like a simple binomial distribution. And the way that you calculate the probability is using this hard sigmoid function. So they have these two different ways that they binarize values. In terms of how they are actually binarizing everything, is what they do is for the weights of the network, they just clip them to be they clip them to be -1 or 1, or not clip them, but they make them. I guess you could say they use the sign function. I think they say they clip it later. I'm not sure. And then what happens is you get your input, which is a real valued input. It could be an image, it could be a vector, and you put it through the layers, and at each layer you have like your multiplication, like your weight matrix, and then your nonlinearity. And so yeah, go ahead, Damien.
I'm wondering, they mentioned this is a binary neural network, but they also use +1 and -1. And in binary, to represent -1, you need 2 bits of information. You need the sign. So I wonder if, like, how is this actually represented in memory? Is it like -1? Is it a 0? Or
I think that when they're talking about binary networks, they're talking about it more just that the values of everything can be only those 2 values, so binary in that sense, and that they don't really go into well, they do go into don't really go into how they represent things, except that they're representing everything with like in base 2, which is what happens in a computer anyway. So it's not really they don't talk about that.
Right.
They probably can't, since they're approximating everything with -1 and 1. If they change it to 1 and 0, I have a feeling that wouldn't work as well, because since you're doing like all these multiplications, the 0 would just be essentially cutting out that signal.
Yeah.
And so they have to probably use -1 or 1 just to be able to make sure that information is propagated through a neuron, even always propagated through a neuron.
So is this? I guess this is like the 1.58 bit information network that those binary transformers.
So this is not. They're not actually focused on like like how quantized the weights are. They're just saying like, hey, the weights are going to be -1 or 1.
Oh, I see. Okay.
So they're not focused on this. I think this paper is old enough that they haven't really. It's not even about optimizing for like. Well, it is kind of about optimizing for but this is more like of a proof of concept still.
Yeah.
Whereas the further literature is about like actual quantizing, and like where it gets into to the extent where we have like 1.58 bit networks and stuff.
That makes sense. Yeah. Thanks.
So they have these two binarizing functions, sign, and then this probabilistic one. And they say here the stochastic binarization function is more appealing than the sign function, but harder to implement because it requires sampling. And they say that we use the deterministic binarization function at all times, with the exception of activations at train time in some of our experiments. And I was thinking to myself, I would like an explanation of why the stochastic binarization is better, because I was just, I don't actually see why it would be better to binarize everything, like weights and activations and everything, using the stochastic one. If anyone has any ideas, feel free to shout it out. And I'm also like, why? It's interesting to me that they can switch between the two, because they're saying with the exception of activations at train in some experiments, that means that they were able to, like, they would train a model using the stochastic binarization, and then at test time they would use the deterministic one. Yeah, I was interested in that, but don't really know why. Okay, so the key thing this is the function that they're using for everything, and then the key thing is that like both the stochastic and the sine function. We'll start with the sine function. Like a sine function has a derivative of 0 everywhere except at 0, because like if you look at the function, it's going to be -1 until it gets to 0, and then all of a sudden jump up to 1 at 0. And so the point that they make is that like for both of these functions, the gradient at most points is 0, so you can't learn using these binarized these binarization functions. You can't propagate gradients back through them because their gradient is 0. So you need to approximate it. So the question is like, how do you approximate it? I'll come back to this. But so propagating gradients through discretization, as I said, it's usually 0. And so that's where they were like, okay, we're going to use the straight through estimator previously introduced in Hinton's lectures. And so what is the straight through estimator? So say you have this function where q equals sine r, and you want to know, and you assume you have like the gradient of, so c is your cost function, so it's like your loss. Say you know your gradient with respect to your loss with respect to the value q, and you want to know it with respect to r. So what do? So what they do is they say the gradient of r is equal to the gradient of q as long as the absolute value of r is less than or equal to 1. So if it's greater than 1, then no gradient flows through, and if it's less than 1, if the absolute value is less than 1, then gradient flows through, and it's the exact same as q. So that's the straight through, because it's literally propagating the gradient straight through. And they say it's equivalent to propagating gradient through a hard tan function. So backwards, it's as if you use this. If you're looking at the calculating the gradient backwards, it's like using this function in order to, hard tan h function. It's using this function to calculate the gradient, but forward, you're just using the sine function. And two things about this. One, as I said before, this isn't like the actual gradient of the function, but it's the approximation, and it seems to work. And it seems to work pretty well, because I think we found it in a completely different application than the one that we're doing here. So it seems to be something that people use. Never seen it before, though. I don't know if you guys have ever seen it before. But it's one to keep in your hat if you're ever dealing with like some kind of discretization, like in our case, an argmax function. And then one thing that they say here is not canceling the gradients when r is too large significantly worsens performance. This is another thing that I wish there was an explanation for, because I'm curious as to like why this is so basically why is this necessary, this part of the propagation of the gradient where where you just pass it straight through. I'd be really curious to know that. Maybe if I did more research into straight through estimators, I would figure that out. But so that's how they calculate all gradients for everything, is they just use this straight through estimator, which means you say, okay, the value of like going through the binarization function, the gradient of the going through the binarization function is equal to the output gradient. The input gradients is equal to the output gradient as long as the input is less than or equal to 1 in terms of its magnitude. So now we know like this is how they're binarizing everything, and then this is how they're calculating the gradient for everything. They have a little point here about like calculating gradients and maybe the value of it. So they say, as they say here, real valued weights are likely required for stochastic gradient descent to work at all. And that's because if you don't use real valued weights, when you calculate the gradient, then the noise, you can't let the noise average out. So when you're using SGD, the whole idea is that like your batch of data that you're calculating your gradient for is an approximation of your overall data set. And the noise in any one example is averaged out over the data set when you calculate the gradient. So like maybe one example is pushing you in like one direction and another, but like their average direction, or like the average of the direction is the correct one to move in, and the noise averages out. And they're saying like, well, with binary ones, it's probably not possible. Like you probably need this real valued gradient in order to get to perform stochastic gradient descent. But at the same time, they say like, yeah, no, okay, that's the same thing. Yeah, so it's just a point to make. I thought there was something more to it. So we've talked about those two things. Okay, and there's a couple of last things, because like the crux of this whole that what I just explained to you is kind of like the crux of the method. Like, how are we binarizing everything, and then how do we calculate the gradient through it? But there's actually some rubs here, some things that make it that they also, some other problems that they had to address. So one of the problems that they had to address is that they're trying to compress real networks. And at the time that this paper was written, for example, batch norm was like the most common normalization layer in convolutional neural networks and even MLPs. And you also have to perform a batch norm operation if you want to compress these networks. Now, there's a problem here because like the batch normalization operation is not binary, and it's actually really compute. It all actually takes a lot of compute. So they don't say this explicitly, but I think the reason why they had to do what I'm about to show you is that they tried to just binarize everything and keep batch norm the same, and it was a computational bottleneck, because one of their arguments is that like the forward pass of the network is like so much faster when you use our method. But I imagine that it's probably not that much faster if you just keep batch normalization layers the same. So basically they had to figure out a way to binarize binarize is the wrong word. They had to figure out a way to perform batch normalization, but using bit operations instead of using multiplication and division. And that's what's here in algorithm 3. But I just want to show you what a forward pass through the network looks like in terms of another algorithm, so you get an idea of what's going on. So you have your input, which is some vector A0, and then let's ignore this for now. But basically, what happens is you get the first operation, which is like the equivalent of multiplication by your weights, is this XNOR dot product, which is a bit operation to do the multiplication. And then after that, you put it through your batch norm, which is your normalization layer, and then you put it through your sign layer, which is your nonlinearity. And so this batch norm is what they had to figure out how to make into a bit operation, instead of doing what you normally do, where you calculate like the mean and the variance, and you center it, and then you divide by the variance. So how did they do that? What they did is they created an approximation for batch normalization, which they call shift-based normalization. And it's pretty, I mean, I didn't go through all the math, but I think the idea that's there is pretty simple. So what they do is in a normal batch normalization there, this first step is also the same. So you calculate your mean, and then you calculate your variance, which they're having to approximate here. But say you calculate your variance, and then you normalize by it. So this is what this is doing here is what you would do is, like, as you can see here. Sorry, I'm not explaining it well. You calculate your mean. You center your input xi. So you just take remove the mean. I mean, you subtract the mean. And then the last step is you divide by your standard deviation. So divide by square root of this. And that's what would come out of the batch norm. But that division is what I think really slows things down, and what they had to figure out how to make into a bit operation. And so what they do is they calculate this approximate power of 2, which is what they have here. And it gives you like a number. And what this is this is a binary shift, which I had no idea what that was. And so, but this is like some number, like 1, 2, 5, whatever. This is a number represented in a bit in a string of bits, and this is like the shift operation, and it can be left or right depending on whether this is negative or positive. And so, what's a shift operation? Just so I can you can talk about it. So you guys, maybe you got. I have a feeling some people know this, but if you don't, hopefully you find it interesting. So a shift operation is literally that you take your original binary number, like you see here, and you just shift it by one place. So you originally had like a 5-bit number, and now you make it a 6-bit number where you shift all the numbers and you just add a 0 at the end. This is called a left shift. And what this is this is equivalent to multiplying the number by 2. So if you multiply any binary number by 2, it's literally just shifting everything 1. And then if you divide by 2, it's shifting everything to the right. So left shift is multiply by 2, right shift is divide by 2. And this shifting operation, I'm guessing, is like a lot more computationally efficient than actual multiplication, maybe because that's what happens under the hood, and you have to do multiple of these. What's going on here is like this number, this AP2, it's like -2 or 1 or 3. And it's the number of shifts that you have to perform to your centered number. And that's how they avoid having to do like the full-on variance calculation over here, and then again having to do the full-on division over here. So that's how they make batch normalization compute efficient and based on bit operations. So that's one thing they had to do, besides just showing you how to binarize and calculate the gradient. They had to figure out how to like perform batch normalization in terms of bit operations. And then the other thing they had to do is they found that Atom was like a really good optimizer, as we all know, for training neural networks. And they wanted to be able to perform Atom. But again, that creates this bottleneck at training time where everything's being done in terms of bit operations except for Atom, which is like a ton of multiplication. And so again, what they do is they figure out how to do the whole thing, approximate the whole thing using bit operations, and that's what's over here. But I'm not going to go into it because the main thing I'm hoping that you guys get out of this, if you didn't know it, is that the way that you can do multiplication using bit operations is by doing these left and right shifts. That's like the crux of it, and that's how they do it here, which I thought was pretty interesting. I didn't know that. So, and just to like say it again, like a left shift, binary shift means you're multiplying by 2, and a right shift means you're dividing by 2.
So this is probably a very stupid question, but after this normalization, isn't it not binary anymore?
Yeah. Oh, so good. But no, that's not a stupid question. That's a good question, because I was thinking the same thing. I was thinking like, okay, everything is binary, right? But no, everything isn't binary. What it is that, so see where there's a B? in this. So this is like the layers of the network and going through. Wherever there's a B, that's actually a binary number. But the other numbers are just normal numbers. But they're what they do is that they like take these operations. They do everything in terms of bit operations instead of just doing multiplication on top of it to speed things up. Because otherwise, a lot of their claims about speeding things up wouldn't really work. But yeah, so the output of like the multiplication layer or the weight multiplication layer is a normal number, and then the output of the activation layer is a binary number.
Yep.
And the output of the overall network, you can see here that they actually don't, is also a normal number. It's not a binary number. It's just whenever there's a B on top, it's binary. And there's one last issue. So the way that they do, they're doing, they're approximating the weight multiplication is using this XNOR dot product, which is again a bit operation that you can approximate matrix multiplication, but it only works if the values are binarized. So both the input here has to be binary and the output here has to be binary. And that's true for all of the intermediate layers of the network, because you know that the output, the activations are binary, but the input to the actual network, like A0, is not binary. So they also had to come up with a way to deal with that, and that's like the last part of their method. And that's what algorithm 4 is actually, but it's easier to explain here. So say you convert your input into an 8-bit fixed point number. I actually don't know why it has to be fixed point, but maybe that's just like makes it way easier and faster to compute. So you could either, here's your weight matrix, and here like one row of your weight matrix, and here's your input, and this is how you calculate the output. And so this is one way to do it. But the other way to do it is to, like, as I say, convert this to a fixed point floating number. And then n indicates like the value at that bit position. So say if we go back here, this is your number, and n is 2, then your value is 0. So xn is 2, x of 2 is actually 0 here. And then you multiply it by your binarized weight, which is 0 or 1. And then you have to multiply it by a power of 2 to get like the actual value, since that's what's being expressed here. Like, you know, this, if you just had these first two numbers, then this is actually expressing 1. So that's why you have this. So that's how they deal with the fact that their input isn't binarized, and they make everything, and that's how they make everything done by bit operations.
I know why it has to be a fixed point floating operator,
Okay.
and that's because you can use your left shift and right shift on them, and it still works.
You can use what? Sorry, I didn't hear you.
You can do the bitwise left shift and right shift on them, and it works.
Ah, okay.
With floating point, you can't.
Learning a lot about computer architecture stuff, or low-level computer operations. Cool. So that's the whole method. We covered a lot, but again, just to go through the three things, it's the binarizing function, the straight-through approximator to approximate it, then how to do batch normalization using shift operations, and then over here it was how do we take a non-binary number and then use binary operations, like bit operations, in order to calculate the output. They still have to do some multiplication, as you can see here in this one, which is what they're trying to avoid everywhere. But what they say is the first layer, especially in computer vision, usually has fewer channels, and basically the first layer is the smallest and the input is the smallest, so it's not a large part of the computation, so you don't have to worry about it too much in terms of it like being a bottleneck for computation, because everything they're doing here is to make the forward pass more compute efficient. Okay, so now let's look at some results, unless anyone has any questions about the method.
I'm tempted to ask you to explain the straight-through processing again.
Yeah, sure.
I missed a step somewhere.
Yeah, let's do it. I'm actually gonna. So so the function would be like q is equal to sine of r. And then what they're saying is that the gradient of q, let's see if I can do this. Oh, no, I can't. So I'm just going to have to do it this way. The gradient of q, and what they're saying is equal to the gradient of r times 1. Well, it's actually like 1 if the magnitude of r is less than or equal to 1, else 0. And so the way that works is that say r is equal to 10, then your gradient is going to be 0.
Okay.
Is going to be 0 because even if g of q is, I don't know, 3, because of this like if else statement here. But say that wasn't the case, then it's literally whatever GQ is, then that's what GR is. So if GQ is 3, then GR is 3. And so, and the way that would work is like maybe say R comes in as, I can give you the example from the argmax thing that we were talking about before. So, so argmax is like you have a set of probabilities of 0.3, 0.2, 0.5. And then your argmax is equal to 0, 0, 1. I mean, or you could represent it as an index, and then it's equal to 2. But let's put it this way because I think it makes more sense, and it shows you how they use this in the application that we were doing. So going from here to here, from probs to argmax, is not differentiable. But what you can do actually, like the way you get this gradient to work is what you can do is you can say, let's make this x and make this p. And what you can do is you can say x is equal to x minus p plus p. And still, okay, that wouldn't allow you to propagate your gradients through. But what you can do is you can say x is equal to x minus p dot detach plus p. And what that does is it means that like your probabilities are you like if when you do detach, you're saying take this out of the computational graph. So like don't calculate gradients for this. Okay. So you can, in terms of the gradients, you can it would literally be this because you've taken out that other part. And so you're saying x is equal to p, and so you know that the gradient of p is equal to the gradient of x. So actually, I just explained the trick for it, how you do it in code, but I don't feel like I've explained.
It's interesting. The 1 in the approximation, like that we have the radius of 1 essentially, where we have non-zero gradient. Is there like a justification word, or could it be any number really? Because
it could be any number.
Yeah, because only for the sign you would say it's technically like some delta function, right? So the function that has a finite integral but is infinitely thin, if you will. And here they sort of approached the delta function with, or distribution with something that is like a finite width, which happens to be 1 for some reason, but it's kind of whether there's some deeper rationale for that, or whether there's some amplification properties. Also sometimes there are these interesting things.
Yeah, I think in this case, based on what I've seen and talking to Yarn about it, it's like this is a trick people use, but there's no good justification for it, really. They just propagate through the gradients through the network. I've actually seen it before with quantized variational autoencoders. So I've seen them do the exact same thing, where what happens is you have to choose, you have like a set of 10. No, I'm not going to get into it because I don't want to make too much, I don't want to deviate too much from the topic that we're talking about, but I've seen it somewhere else too, this kind of idea of just literally, it's called the straight through estimator, because you're just saying, okay, the gradient of the output is equal to the gradient of the input. I don't care what the function was.
And is it, it almost seemed in the first example you typed out that actually the gradient is 1, unless the value is greater than 1, at which point it's 0. So when you're going backwards through the network, you're not going to explode the values of weights, because the else 0, and you're just using the gradient of 1 everywhere else, just as to, it lets signal flow through.
So, yeah, exactly.
So it's quite simple. It's quite explainable. Yeah, nice.
Except for the fact that I would like an explanation of what happens, because it said that like it's really bad for performance if you let them grow past 1.
Yeah.
And I would like an explanation of why, because later they also say it's just like if it's greater than 1, then since you're using the sign function to binarize things, it really doesn't matter,
Okay. Yeah, I see what you're saying. Yeah, because I can see if you're using floating point numbers, what you get if you're outside that negative 1 to 1 range, you're going to get a gradient of 10, and then you're going to really explode your weights going back through the network.
Yeah, I'm not sure. It's definitely something where you have to have experience with it to know what these things look like. Because, like I said, there's a couple of things that I underlined, and I was like, I wish there was an explanation of this. Like, why is the stochastic binarization more appealing? Why is not canceling the gradient when R is too large worse for performance? But maybe if you're in the field of quantization, but if you're not, then you don't. Well, I don't. So I'm guessing if you're not, then you don't. Okay. Results.
Thank you.
Yeah, of course. It's nicer when we have a discussion and talk about things. And I usually have a lot of questions about the paper that I don't have time to figure out myself, so it's good to hear what other people think. So they have 2 sets of results in terms of performance. So the first thing that they're focusing on in terms of results is like, how good is this new method in comparison with existing methods at performing these tasks? And they have the 2 sets of results are on like the class. I guess at the time there was a set of 3 data sets that were the classic data sets for benchmarking your new method, which was MNIST, SVHN, and CFAR10. And then they also have results for ImageNet, which at the time, like the results of all these other like previous methods were so poor that they didn't even really, they don't report on ImageNet. And so this paper was the first one to report results on ImageNet. But what you can, so this is their method, BNN, and they have they have like distinctions between the different methods of like, is there binarized activations and weights, and is it at training and test time? So like these methods are all binarized activations and weights at training and test. These are binarized but no binarized weights, but no activations, and so on. And one thing I found interesting is that in terms of and by the way, lower is better. It's test rate classification error. One thing I found interesting is like all of the other methods pretty much perform on par. But the point here is like there's a ton of numbers here. The point is that they perform around the same level as no regularization. I think that's the main point. And when they're using Theano to train on MNIST, they perform better than all of the other methods. But if they're using Torch 7, they perform a little bit worse than some of the other methods. And they actually also perform worse than this binary connect on the other two data sets. But overall, I think the whole point is that it's that they perform comparably to as if you had your best performing network, or like no quantization. Yeah. Don't. No, not really. Yeah, comparable results. I guess one thing I was thinking is the results are a little bit of a mixed bag for me because they're not always doing better than the previous methods. But I guess that means that the reviewers also felt like the novelty of the method is worth publishing, despite the fact that the results aren't like clearly better, just partially better.
Well, the novelty is, sorry, the advantage is the lower computation cost, isn't it?
Yeah, there's a couple like that they argue for. Like they argue for energy efficiency, computation cost. We'll go over them because that's the second part of it. And then the whole thing is like comparable performance. So on ImageNet, they have like their results are they get 36% accuracy at top 1 and 60% accuracy at top 5 using AlexNet, and so these performances leave, as I say, while these performances leave room for improvement relative to full precision nets, they are far better than previous attempts to compress ImageNet architectures using less than 4-bit precision for weights. So this is, I guess, where they have like the real improvement that you don't see in these other data sets. Where they're like, okay, well, this is by far the best. And then they go on to talk about how they have a follow-up work where they don't use 1-bit quantization, but they use 6-bit, and they get comparable results all of a sudden. I thought it was interesting that they must have added that in afterwards. That like we have this other paper that just came out where we're not doing 1-bit and we're getting great results with it. If you look at these are the training curves for training on CFAR 10, and their method actually takes much longer to train. And so that was one thing that really confused the fact that it took longer to train was because if you look at something, one thing that they're really harping on is that they are doing binarization at training and test time. And I'm wondering to myself, what's the value of doing that if it's of binarizing at training time if it's slower than just normal training? Like, what is it? Would it still be slower if you didn't binarize at training time and only at test time? Or like what is the other value of binarizing at training time that I'm not seeing besides, because it's obviously not speed. And so I looked through the whole paper for the answer to that. And the only thing that they say over here is that the only thing they say is that they say it somewhere, but I'm not going to find it that easily, is that they have a faster forward pass during training time, like a much faster forward pass, but I guess the backward pass is slower because the architecture isn't optimized for it. Like the chip architecture isn't optimized for this. The hardware isn't. So maybe it's the opportunity for faster training that they. I don't know, because that was one thing about the paper that I wasn't sure of. But I'm also sure that that's something that a reviewer would ask. So I think I'm missing something, or that I think I'm missing something. But so, okay, we went through performance, comparable performance. So the next thing that they talk about is that the amount of memory and first they talk about the amount of how much more efficient in terms of energy usage the forward pass is. And so they just show you some numbers for what they're doing, and basically they are able to reduce the energy consumption by like a factor of 10 or 20. Like for some parts, they can reduce the energy consumption by 32 by doing all of these bit operations instead of doing multiplication. So yeah, that's one of the benefits, is like a reduction in power usage. Not speed. They're not talking about speed, just power usage here. And then the other thing is that they pointed out how you could do all of the operations on a GPU, but you would need to, like, how you could do the operations, but you'd have to like write your own kernel. So they do write their own kernel for it, and they get like a 7x speed up in the performance in terms of like performing the forward pass. And so the other argument that they have is that their forward pass is much faster. Okay. Okay, and then in terms of limitations of the method, in terms of full binarizing, is that they say that we have to save the full precision, the value of the full precision weights during training, and this has like this is the remaining computational bottleneck during training, since it's an energy consuming operation. And yeah, that's the paper overall. Comparable performance, and then much less power usage, faster forward pass, backward pass is pretty slow, it seems. Or it's that maybe the backward pass isn't slow, and it's just that you have to train for a lot longer because you're constraining everything to be binary weights. I don't know. But it's a cool paper, and I feel like I learned a lot from it, and I like that it wasn't very math heavy.
Mm. I looked for follow-on work that used the distilled networks down into this format, and I didn't find. I only just started, but I didn't find any in that short look that I did, because I figured that this would be useful for people to like distill a large language model down into a binarized form if it, if you didn't lose too much performance.
Yeah, that's a good point. I think what it is that they probably just can't get the performance they need when they make it binary, and so they do like 8-bit or 4-bit, or as Damien was pointing out, like the 1.58-bit one.
Yeah. This is absolutely right.
But that's why I said I think this paper has been cited so much that I think it might be like the original paper, or the paper that everyone likes to cite on quantizing, maybe, because I was also wondering, like, maybe they use some version of the straight through estimator when they're training quantized models. I'm not sure. Maybe it's like, because I'd never heard of the straight through estimator until last week, but maybe it's being used. It's like the most pervasive gradient approximation used ever, and it's used everywhere to train language models, quantized language models, and we don't know. So if anyone finds out, let me know. Are there any other questions? Okay. Well, if not, thanks everyone for coming. And Ben is presenting next week. We haven't decided on a paper, but I'll post it as soon as we know. And I hope everyone has a good weekend.
Thank you, you too.
Thank you very much. It was very good.
Thanks, Peter.